We've already gotten ourselves pretty far on this list of objectives here. Solving polynomial and rational inequalities using sign charts, algebraic techniques, graphical techniques. Really, we've done all of that at this point. We just need to see some that are a little bit outside the box, and that we'll see more of that today. And then solve real-world problems using inequalities. Definitely the last two that we'll work on today will meet that part of the objective. So, yesterday, we were right here. And I was waiting for any latecomers to come on. And then I know that there are some people that you have really bad Wi-Fi, so then you pop off and go listen to the lesson. So, hopefully, you will listen to this because we have to remind you about registration. Registration opens today or tomorrow. Yeah, one of these 2 days here. And anybody who is successful in pre-calculus should be registering for Calc AB next year. So as you do your registration, if you're doing well in pre-calculus, you should be thinking about Calc AB. Then if you're not, email me and let's talk about it, because you have a couple of things that you could choose to do. There is an AP Stats course that if you're really good in English, the English class, then that would be an alternative. But anybody that's being successful in pre-calculus should absolutely be signing up for Calc AB. So like I said, yesterday we talked a lot about that first objective, figuring these out algebraically, analytically, graphically, and this was the last one we did here, and this was rational. We had our little 2x plus 1 over the quantity x plus 3 times x minus 1. And we knew it was going to be hyperbolic, so we expected branches and all of that good stuff. But the piece that was really helpful here was the sign chart in order for us to figure out, hey, if I know this is the 0, and I know that it has to go up between -3 and -1/2, and it has to go down between -1/2 and 1, well, I know what that little piece is going to look like. And we could draw that in there. Now, of course, that would be for draw or sketch. That wouldn't be for graph. For graph, we'd actually grab the graphing calculator and find some points. And then out here, it helped us figure out where the branches were going to be. We knew everything would be negative as we go to the left of -3, and everything would be positive as we go to the right. Now, the reason I'm going back to that problem is because we get to example 6. And we have to use that mathematics skill that I've talked about a lot, and that is, well, if I knew how to do that one, what could I do to this one to make it look like that one? And the answer would be, if I can get this to be one fraction, then I'll be able to do this. Because I want to keep that less than 0 on that side. I don't want to mess with that at all, because I need that 0 in order to talk about my solutions. So what I'd have to do is go ahead and add those two fractions. But of course, when you're adding fractions, you need common denominators and all that good stuff. So let me rewrite this. And let me give myself a little bit more room. So with these two, our denominators are already in factored form. So we take a look and say, well, the LCD would be both of them. We're going to need them both, and their highest power is 1. So the first fraction would need an x minus 1 for the numerator and the denominator to make that happen. And the second one would need a little x plus 3 on the numerator and denominator to make that happen. Now remember, our goal is one fraction, so it looks just like the problem that we just did. So let's distribute the 5. And then in the second fraction, we'll distribute the 3. And now that we have a common denominator, let's put those together and see what we have. Now this is interesting because I look at my numerator and I realize, well, I could factor a 4 out of that. And if I do that, I have kind of a little deja vu moment. 4 times the quantity 2x plus 1 over the quantity x minus 1 times the quantity x plus 3. All this is missing is the 4. So this example that we just did, example 5, if we multiply it by 4, we get this one. So then I think, would it be okay if I just divided 4 from both sides of this and used the math from the last one? And the answer is yes, because that's not going to flip our sign. It's not going to make anything weird happen at all, so we could do that. But just so that we remember what we're really supposed to do, we think about where those zeros and those asymptotes are going to be. So our 0 for the numerator, because 2x plus 1 would have to equal 0, will be a negative 1/2. And then the zeros for the denominator that are not going to cancel are going to be our asymptotes, so negative 3 and 1. We get those on our sign chart. Again, the spacing between them doesn't matter. We just need that to see what's positive, what's negative, and all the good stuff that we need. So now, I put something to the left of negative 3 in here, and I just want to see, are we going to get positive or are we going to get negative? What's going to happen? So if I were to put a negative 4 in here, this would be negative, this would be negative, and this would be negative. So to the left of negative 3 would give me a negative result. There's 3 negatives there. Between negative 3 and negative 1/2, I'll pick negative 2. My numerator is still going to be negative. Negative 2, this will be negative. But negative 2 plus 3 will become positive. And now, since I have an even amount of negatives, that's going to be positive. Something between negative 1/2 and 1 that's nice to work with? 0, of course. So now we'll have positive, negative, positive. Odd number of negatives yields negative. And then to the right of 1, something like 2, something small. Positive, positive, positive. And we have it again. So now we have to answer the question, which was, when will this be less than 0? So here's where I had mentioned yesterday, it's a really good idea, since we're starting to get more involved here with vertical asymptotes and zeros on there, for you to make a dot on the zeros on your number line, and that was our negative 1/2. So that distinguishes that from the negative 3 and the 1, in case we forget that those were vertical asymptotes. Now, when is this less than 0? Would be when it's negative. So that's going to be to the right of negative 3. And we have another little section here that's going to be negative, and that's our negative 1/2 to 1. So like I said, if you noticed, the only difference here is they multiplied by 4. Well, then maybe you don't redo everything, because you could divide both sides by 4 and you could use the same graph and everything that we had before, except it would have, like I said, that 4 in it. So what I want to show you about this one, even though it doesn't say to graph it or sketch it, is the difference between this graph and the one we did yesterday. Is just going to be that it's vertically stretched. You know, we've got a 4 in front of there, so it's going to be vertically stretched. But as far as our signs go, it's going to follow the exact same positive and negative features and the exact same zeros and vertical asymptotes that we had with this one yesterday. So nothing new in that graph except for the fact that we had the 4. So vertical stretch. All right. So definitely using a variety. I mean, we have algebra here. We are thinking analytically as we go through it, and then we're kind of checking with our graphing calculator, does all of this make sense? We get to example 7, and this is where, like I said, we start to see some unique ones. So today is about seeing some that maybe we don't have quite as good a feel for what it's going to look like when we graph it. And this is solving an inequality involving a radical. So we have the quantity x minus 3 times the square root of x plus 1, and we want to know when is that greater than or equal to 0. Well, it's already in factored form for us, but we have something different this time. I know the 0 for this one would be x equals 3, so there's a 0. But I also know in order to graph this in the real world, I have to have that be greater than or equal to 0, because otherwise we're going to have imaginaries in there. So we'd subtract 1 from both sides. Now that is different. So when we make our sign chart, we know we have significant things happening at -1 and at 3. And we know that 3 was a 0. But here's what's really important. We can't use any of these x's that are to the left of -1. So it'd be a good idea to put undefined in here, and then think about that -1, about whether or not that's something we can use. Is it something special? Well, the square root of -1 plus 1, that's going to be 0. So this is another 0. So this crazy little graph that has x minus 3 as a factor and then a square root also with it is going to cross the x-axis at -1 and at 3. So now we would want to know, well, what about the positives and negatives? What's going to happen? So if I choose a number between -1 and 3, like 0, which is nice, go back up here, 0 minus 3, that's going to be negative. 0 plus 1, that's going to be positive. So that portion of the graph is going to be below the x-axis. Then I pick something that's not too hard to work with on the right side of 3, so maybe I just go with 4. And now x minus 3, 4 minus 3 will be positive. And anything positive in here is going to give us a positive. So now, what should I expect? Well, remember, square roots have that half curve thing going on. But we also have that x minus 3 in front, and we haven't experienced those two things happening before. We could answer this question without seeing the graph right now, so maybe we ought to get that out of the way before we forget about it, because we just needed to know, when is this greater than or equal to 0? And we have already figured out 2 spots where it's going to be equal to 0. At -1, but now greater than or equal to 0 would include the 3 and to the right forever. But I would really want to see this graph. I would want to see, what does that look like when you have a linear portion to it and you have a square root portion. And so I typed in the x minus 3 and then the square root of x plus 1. And I'll just turn that on. Hopefully you have your graphing calculators with. Now would be a good time for you to punch that in while I mess with this big behemoth. And then we'll hit zoom 6. Now, this is really important. We know this is a graph or error. Our algebra told us that should go all the way up. And remember, when we've worked with square roots before, sometimes the graphing calculator doesn't give the full picture. So we could do a lot of zooming in on that to make sure it works, but our algebra already supports the fact that this should really go all the way up to -1, 0. So interesting little graph. Linear and square root together. And what's really nice about it is that our sign chart supported that. so that we knew, hey, there's a graph for error here. It should be going all the way up to negative 1, 0. So, like it said, use a sign chart, did that, and then we checked our solution graphically. So you can see how that objective, again, of algebra, analytics, and graphically totally working together here on any of these problems that we look at, but especially the ones where we're saying, wow, something linear and a square root, not sure what that's going to look like. It helps us to get more and more pieces of what we're going to see when we graph it. Well, here's another one. Solving an inequality involving absolute value. Look at that little weirdo. So now we have linear being divided by absolute value. Wowzers. Okay, let's see here. Well, we can find the 0 for the numerator. It's going to be 2. So that's a 0. And we can see on the bottom we're not going to be able to use negative 3 because negative 3 plus 3 would give us 0, and then we'd have a 0 in the denominator. So then we go to our sign chart. And we realize we've got a 2 and a negative 3 to put on here. And we just want to figure out the positive, negative, and all that good stuff. So to the left of negative 3, well, something like negative 4. Negative 4 minus 2, that's going to be negative. Well, whatever I put in this denominator, the absolute value is going to make sure it comes out positive. And a negative divided by a positive is going to be a negative. Then I need something between negative 3 and 2 that's not too hard to work with. Well, that's 0. So if I put a 0 up here, I'm going to get a negative on the top. And the bottom, again, we're guaranteed, is going to be positive. So we get 2 negatives there. Must be doing something interesting on that portion of the graph. Then 2. So I'll pick something like 3 that's to the right of it. So now we'll get positive over positive, which will be positive. Well, we can definitely answer the question at this point because this was less than or equal to 0. So I'd like to give you a moment to write your answers down. And then I want to put you in a breakout room so you can check your answers with others before I ask somebody what they have for an answer. So you'll feel some confidence here. Just checking in to make sure you're talking to each other and checking your answers. Heard what we were supposed to find. I heard talking. That's good. So we're trying to find the solutions here. You'll notice I did not put the little dot on the sign chart. So figure out if there should be a dot for a 0 there, and then talk about your solutions, everybody.
Okay.
What you want to do is figure out where should the dot be on the sign chart, and then somebody be brave enough to tell everybody what they had for an answer so that you can talk about it, please. Okay, total quiet. I don't know if that means you have this or not. What I want you to do is go back and figure out where the dot should be on your sign chart. And then once you have a solution, be the brave one that tells everybody what you think it is so that you can all talk about it, please. I don't know if you two already had this conversation or not, but talk about where the dot would go on the sign chart, and then be the brave one that says, this is what I got for an answer, and discuss that for, well, a few seconds, please.
Okay. So
Okay, it's looking good, like I've got everybody back. And one of the things that I really wanted you to discuss was, where should the dot go on the sign chart? So can somebody please unmute and tell me where our dot should be?
on the 2.
Right? Needs to be at the 2. The zeros. And that helps us figure out what our answer should be, because we can just look at our sign chart and say, well, here's where things are negative, here's where they're 0. Now, how do we represent that? Which brings me to my next question. Can somebody be brave and tell us what they had for their solution? Does this mean it's too early for brave? Hopefully, in at least one of the groups, you had time to talk about the answer. And hopefully, you felt like, yes, this is what the answer is. So somebody please unmute and tell us what you had.
Okay.
Yeah, go ahead, Rayford. Great.
So I had a negative infinity and to a negative 3, not including negative 3. Union. Negative 3, not including. And 2 including.
Excellent, Rayford. Excellent. That's exactly right. I mean, here's our negatives, but this was a vertical asymptote at negative 3, so we can't use it. We have to skip over it on the number line. And then we get back on and we go up to 2 and we realize, hey, 2 had a dot on it. This had an equals bar. So now, I want to see what this thing looks like, because we've got a vertical asymptote at x equals negative 3, and we have a 0 at 2. So a mixture of linear and absolute value. What does that look like? Now I punched this one in, but I think I'm going to punch it in again because I'm worried that we haven't used absolute value in a while, and it's possible that people may have forgotten how to get that on there. So parentheses, x minus 2, parentheses, and we need to divide it because this was a fraction. And then we have to find absolute value, and that's going to be math, arrow over to the right to numbers, and number 1. And this actually has the new fancy one. My one for the TV always had parentheses, but this one has the nice absolute value symbol. So you punch it in and you hit graph, and that is a very unique hyperbolic function there because we had the linear portion and then we had the absolute value portion for that. And people are always shocked that there are negatives with this because of the absolute value. But remember, it wasn't absolute value for the entire thing. It was absolute value for the denominator. So we can still get negatives, and obviously we did get negatives. But again, our sign chart would have given us a picture of this because we definitely have the negative, and the positive. So we can get a feel for it before we graph it. That's a good one. Now, that last part to our objective, the last chunk of information that we have here, deals with real world situations. So Dixie Packaging Company has contracted with another firm to design boxes with a volume of at least 600 cubic inches. Squares are still to be cut from the corners of a 20 by 25 inch piece of cardboard. I'm going to fold up the flaps to make an open box. What size squares should be cut from the cardboard? So we've seen these problems quite a bit. Well, it doesn't really look rectangular since that side was. All right, there we are. So we've got 25 by 20 inches. We don't know what these are. And we have to set this up. Well, it says a volume. So we try to think, well, boxes are going to be length times width times height. So it was 25, but they're going to cut an x off here and an x off here. So that'll be 25 minus 2x. This was 20, but they're going to cut an x off of here and an x off of here. So 20 minus 2x. And when we fold it up, this little flap will be the height. So that's x. Now, what did they say about that volume? It has to be at least 600. Well, 600 is at least 600, so we could use an equals bar on that one. But at least tells us it could be 601, 602, 603, so greater than or equal to 600. Now here's the good news. We don't even have to multiply this out. The calculator will do this for us. All we have to do is say this side is y sub 1, this side is y sub 2, and see where they're going to hit each other. And we should be good to go. But it's the window that usually messes people up because they're like, what should I use for my x's and what should I use for my y's? Well, don't forget, we talked about domain before. Domain is the x's. And we said you can figure that out by finding the zeros of your factors. So if we have 25 minus 2x equals 0, well, we're going to have to subtract 25, and then we're going to divide by negative 2. So we're saying 25 halves would work for that one. But we find a smaller 0 when we go after 20 minus 2x. So we could subtract 20, divide by negative 2. Now what that's saying is, if we were to put 25 halves in each of these, this one would be a 0, this one would be negative, and we know that's not possible. You can't have a negative length or width. So we'd want to use the 10 because that would ensure this is positive, this would be 0. We don't need to worry about that one. That's going to be that height for the box right there. So our x's, 0 to 10, maybe a little bit extra for some room. And then our y's, that's made so much easier by the fact that we know what the cutoff has to be. The cutoff has to be 600. So that means we need to see at least from 0 to 600, but we'll probably go a little bit farther so we can see the intersection. So into the calculator we go. So definitely the objective about graphically is going to be used here. And I want to see when do those two hit. So yeah, mine is not going to be y sub 1 and y sub 2, but I'm just using the ones that I already have turned on. Window, 0 to, I'll do 15 since we said we know it has to go to at least 10. And then our y's, I'll try 700. I really want to see a clear picture of here's where they hit each other. And there it is. Now, I also realized this looks like it has 3 answers. But remember when I did my window, I went from 0 to 15. So this answer way out here, that would make negative dimensions for my box. I'm not going to use that one. Or I say, you know what, since I know it's 10, let me just change my window to 11. And then I won't even have to worry about the spare one that's out there. So those are the kinds of choices that you decide to make graphically, just so that you don't use some solutions that we see up there that you shouldn't be using. But there's 2 of them. So let's take a peek and see what we can find. Second trace, number 5. And I always do the left one first. If you want to, do the right one and then come back and do the left one. Totally up to you. So I'm moving Blinky over here by that intersection. And Blinky says 1.659 with rounding. And then the other one. Second trace, number 2. There it is. Enter, enter, enter. Uh-oh. Try that again. Second trace, number 2. Blinky should be over there. Probably too close to the intersection, so it was freaking out. Well, if I hit number 5 instead of number 2, then I'll be better off. There we go. 6.159. So, what I know is this one rounded to 1.659. The second one there is 6.159. And this problem was about at least 600. Well, that's this up here. And these 2 numbers that we just found. Because this is perfectly 600. And everything that's above that is more than 600. So that's going to meet our at least. So our answer has to include the 1.659 and the 6.519. But we also need everything that's in between it because that would be greater than. So we need some square brackets to tell people that 1.659 is included and 6.159 is included. Whoops. And then we'd want to go ahead and make a sketch, which is where my head was at right now. So maybe something along this line. There's your 600. So that when you look at your notes later, it would make perfect sense. In fact, you might want to put these on here too. So it matches what we saw with our graphing calculator. Now, those were not nice decimals. which means if we had decided, hey, I'm going to multiply all this out, I'm going to subtract 600, and I'm just going to try and factor this, it wouldn't have worked. I mean, those are nasty numbers. If when we had found these, they were fractions, decimals that we recognized as fractions, then we would know, hey, I can do this one algebraically. This is going to work. But not this one, and usually not with a lot of word problems. You know, we end up with a lot of decimals. Alrighty, example 10, designing a juice can, revisited. So we're talking about the juice can again. Tomato juice, in fact, same one. Stewart Cannery will package tomato juice in a 2-liter, 2,000 cubic centimeter cylindrical cans. Find the radius and height of the cans if the cans have a surface area that's less than 1,000 square centimeters. Okay, well, the first thing they gave me was volume. Volume of a cylinder is pi r squared h, because the area of your bottom, your circle, would be pi r squared, and then you have to multiply that by the height. It has to be three-dimensional. Well, they said this was 2,000. Well, that's no good. That's two variables. So I better take a look at that surface area formula again. So surface area formula, just think, okay, I need the top and the bottom, so that's going to be 2 of the pi r squareds. And then I'm going to need to know the area of the sides, which are circular, so that's going to be 2 pi rh. Circumference times the height. Well, let's see what they tell us about that. They told us that it is less than 1,000. So 2 pi r squared plus 2 pi rh is going to be less than 1,000. Well, again, too many variables. I'm supposed to solve these with one variable. But we remember back to this problem, and remember we had to fix this so we could substitute in to what we have in the blue here. I want you to take a look at this. And I want you to, hopefully you'll remember, hopefully you'll think about this and analyze it. Which would be easier to substitute in for, R or H? And then please unmute and tell me your thoughts. Yeah, there's only one of them. I mean, that's going to make it much easier. So let's get H by itself. And then we'll substitute it in. So 2 pi r squared plus 2 pi r times our 2,000 over pi r squared is less than 1,000. And then we can do a little simplifying. So 2 pi r squared plus the pi's will cancel out, one of the r's will cancel out, and we will have 4,000 over r. And now I think that looks a lot like the problem that we just did. So maybe I'll stop right here and put this in as y sub 1 and y sub 2. Because it's highly doubtful that if I multiply everything by r, that I'm going to be able to factor this, because I would have a cubic in the front and I would only have 3 terms. So again, usually with the word problems, it's better to just grab the graphing calculator and see what's going on. So while I erase and get set, you can go ahead and punch that in. Remembering there is a pi key on there, second, and the caret symbol right above the division symbol there. So now, probably going to have to change my window a little bit. And again, this is a tomato juice can. I really can't see them making it, have a radius that's super large. But all of this was in centimeters, so I'm going to go with 20 centimeters. And I have to be able to see the 1,000 square centimeters. So I'll go with 1,100. Looks like we have two solutions. So we'll investigate both of those. Let's see what they are. Second trace, number 5. Where's Blinky? Well, I'll do the right one first this time. Blinky likes that right side first. We'll do that one first. So 9.655. And then the other. 4.619. And this one said that we want it to be less than 1,000 square centimeters. So here's our 1,000. We think about how that's below. So let's see if we can give them an answer here. So from 4.619 to 9.655. But can we include those two this time? Somebody unmute and let me know what you think about that. Can we include those endpoints this time?
You cannot.
Why is that, Ben?
Because it's less than 1,000.
Excellent.
Less than equal to.
Excellent. They're not looking for the exact same 1,000. They're saying just less than. So this time we can't include it. Now, this makes this interesting because this time they wanted to know the radius and the height. So what we just found was the radius. But good news, we have a really good formula up here for height. 2,000 divided by pi r squared. And I don't want to make you sit in here and watch me type 2,000 divided by pi times 4.619 squared. But remember that when you have more than one term in the denominator, you should always use parentheses right here. And it really, numerator or denominator, if you have more than one term, you should use parentheses. So our height, the lowest one will be 6.829. And the highest one, which would actually have the lowest radius here, would be 29.839. So that would give us their radius and height to make this happen. And again, this is the kind of thing that happens right outside Elk River. There is a place called ProTech Engineering that makes machines to do exactly this, to figure out, how do we get this into a can that will meet all the specifications that the manufacturer wants. We've got actually quite a lot of those, not in Elk River, but quite a lot of those in Minnesota, those packaging places. So definitely went through all of our objectives today because I see there are more people here than there were when we started. I want to mention registration one more time because you're supposed to be registering for your classes. I think it opened today. It might not open till tomorrow. Check your emails. But if you're being successful in pre-calculus, you should be taking Calc AB next year. If you feel like that's going to be a stretch for you, I need to let you know right now, calculus is easier than pre-calculus because calculus is focused on just calculus, while pre-calculus covers a broad stretch of topics. So it's definitely, if you talk to people that are in Calculus AB, they're going to tell you, yeah, it's easier than pre-calculus. But you have to get through pre-calculus to know what do you want to do in the future. So if you're thinking maybe not such a math-based course, because I don't think I'm going to go into math, remember that AP Stats is out there too, and every major requires stats. So that's another place to go. And again, if you have any questions about, the field you're going into, what you should register for, all of that, email me and we'll email back and forth and talk about the good options for you. So there is day 2. And I will mention, if you're writing that down, if you're feeling like, you know what, I'm probably not going to be able to take pre-calc second semester because I'm not doing real well right now. Remember that college algebra is another course that you can actually get some college credit for, but it's a little bit below pre-calculus. So, like I said, if you have specific questions, email me and we'll talk about it. But that's it. That's actually it for the material from Chapter 2, because we're going to start reviewing tomorrow and the next day. I'll have you just, pop in on the Google Meet. So as far as attendance goes, that way I'll have a record that you were in class, just in case you forget to mark yourself present. And then if anybody has questions on anything, I'll be available tomorrow to answer any of those questions. So. Got about 3 minutes left or so.